Hello everyone, welcome to the third online lecture for design of experiments. In today's lecture, we'll review some of the concepts about single factor comparative experiments that we have seen in the last lecture. We'll discuss about some of the limitations of t-test when it comes to more than two levels of a factor. And then we'll see a brief introduction to ANOVA or analysis of variance, which is another important statistical technique. We'll talk about different data models in ANOVA, and then we'll look at what is meant by ANOVA partitioning and also about the F distribution that is used in ANOVA. As we have seen in the last lecture, a single factor experiment is one in which we were studying or manipulating only one factor, only one independent factor, right? So if we remember, in the last lecture, the comparative experiment that we studied had just one factor called formulation, and there were two levels of this factor, which was modified mortar and unmodified mortar. Okay, and then we had 10 samples with each of these level, and then we tried to analyze it, right? So this is a simple comparative experiment because in here we are just trying to compare the means of two different levels or two different treatments of a single factor, right? So we can call either two different levels of a factor, or we can just treat these two as two different treatments. So this was a simple case because we had only one factor at two levels, right? But in reality, in real life experiments, it would be a little more complicated than this. Like, we would usually have one factor at more than two levels, or we can also have more than two factors, or probably more than one factor, and with each factor at greater than or equal to two levels. Okay, so it could be either one factor at more than two levels or more than one factor, and each factor would be at more than two different levels, right? So in such cases, it would no longer be a simple comparative experiment. Now, for this case, for this lecture, we would just be focusing on A levels of one single factor. That is, we'll still be studying just one factor, but instead of only two levels, now we'll have greater than two levels. Okay, and these two levels can also be called as different treatments for us. All right, so we'll just generalize it and say A levels of a single factor or A treatments. So in order to understand the concepts in this lecture, we'll make use of another example outlined in the textbook. You can find this on page 66 here. So in this example, we are interested to analyze the relationship between the power setting and the etch rate for a wafer etching tool here. All right. So again, we are just studying only one factor here. So our factor is the power setting. All right. So this is our factor here, and we want to study this factor at four different levels, at four different power settings as outlined here. Okay, and then we want to see what effect does each power setting has on the etch rate. Okay, so for us the response variable is etch rate. So this is our response variable, and our input variable or the variable that we are going to manipulate is the power setting. All right, so you can clearly see the difference here. In the last example, we had only two levels. Now we have four levels here. And at each level, we're going to be taking 5 replications. Okay, that is, we are going to test 5 wafers at each of the power setting, and then we'll note down the corresponding etch rate here. So as you can expect here, in total we'll have 20 runs because we have 4 power settings, and at each of the power setting we want to test with 5 wafers. So this would be 20 runs, or 20 different observations that we can get here. And we'll say that this experiment is replicated 5 times because we are taking 5 measurements, or we are testing 5 wafers at each of the 4 power settings here. All right. Now, one important thing in experiments like this is that the run order should be randomized. That is, We have decided that at each of the power setting we will test 5 different wafers, right? So what we have to do is, the power setting that you test with should be random. I mean, you cannot say that first we'll run or we'll test all the 5 wafers at 160 power setting, and then we'll go to 180. So 5 wafers here, and then at 185 more wafers, and then so on. Because if you do like this, this might have an effect on the machine. Probably as the temperature is gradually increased, the machine might warm up, and it might have a temperature effect on the wafer. We want to isolate any such external factors, because we want to be exclusively studying only the effect of power on the etch rate. So we don't want any such uncontrollable factors affecting our response. So in order to avoid that, what we have to do is, we should randomize that. Maybe first you will start with 160 power setting, and then you'll take one measurement here, and then immediately you'll set your machine to maybe 200 power setting, and then you'll take another measurement here, and then maybe you can go back to 180 and then 200. So it's just random over there, right? So the way we can do that is, first we'll just list out all the possible combinations that we are going to do here, right? So at each of the power setting we have 5 runs here, so in total 20 runs here. Now one simple way to randomize the run order, as we have seen in the previous slide here, is just to take these experimental run numbers and then just list them out randomly like this, right? You can pick any number to be the first test sequence, and you can follow any order here. It doesn't have to follow any pattern. That's how we make it random. Okay. And then, so whatever power level was there corresponding to 14, that you'll set your machine at that power level for your first test. So if we go back here, for 14 our power level was 200. Okay, so that would be your power level for your first run. For your second run, we'll take run number 17 as reference, and if we go back here, our run number 17 had power level 220. So your power level for your second test sequence would be 220. Okay, so in this way you would just randomize your experimental runs. And after we have randomized this, so these are the observations that were noted down here. As you can see, they vary a lot. The minimum is, I don't know, maybe 530 to the maximum is 725. So there's a lot of variability here. It may not be much, but it's pretty obvious that they're varying a little over here. And then if we want to visualize this data to see how the etch rates at different power settings stack up against each other, we can make use of a comparative box plot here, wherein we are plotting 4 box plots, each one for each of the power setting. And it's clear from this graph that as the power setting increases, the etch rate also increases. So maybe there's kind of a linear relationship here, a positive linear relationship between the power setting and the etch rate. And we can also see that within the box plots themselves there is a lot of variability here, right? So not all the box plots have their data evenly distributed about the median. So we cannot say for sure whether the power setting has any effect on the variability within a particular box plot here, because it doesn't follow any pattern here, right? But it's at least useful to understand that, okay, there most probably is a positive linear relationship between the power setting and the etch rate, and we obtain higher etch rates at higher power settings. But what if we want to make further objective inferences beyond this? That is, what if we want to understand how does changing the power change the mean etch rate? Like how does it vary between these two, right? And again, how does it vary between these two and all that stuff? But as we have seen in the last experiment, just looking at one chart, we cannot make any conclusive statements, because this is only for these samples, right? If we take some other samples, if we run the experiment again, maybe our observations might be different and these box plots might be different. And if we want to understand, is there an optimum setting of power level in order to obtain our desired etch rate, right? And how different are the means exactly? Like, is the etch rate at 160 significantly different than the etch rate at 200? or we cannot quantify like how different they are or how significant they are. Okay, so we would have to do an inferential test here again, like how we did t-test in the last example. But then for this case here, the t-test doesn't really help much because we have more than two factor levels. T-test works perfectly fine when our sample size is less than 30, which is the case here, and when the population variance is not known, which is again the case here. But then we have more than two factor levels. This is an important consideration here, right? If you remember, t-test is used to compare two means. Now, if you want to apply t-test here, we can do that, but then we'll have to do a number of t-tests here, right? Because we have four power settings, and we might have, I think, one, two, three, six combinations of these power settings. Okay, so you will have to do six t-tests, which in itself would be very inefficient, right? It will be very time consuming, and also there is a big problem that it might inflate our type 1 error, which is, remember, our type 1 error was nothing but alpha, which was also the significance level, right? So by default our alpha would be 0.05, or our confidence level would be 95% here, right? Which is nothing but 100 times 1 minus alpha into that percentage. So if we assume that we are willing to commit type 1 error 0.5% of the time. That means, say if you compare two means first, say if you compare the means at 160 and 180 power setting, right? The alpha error that you are allowed to commit here is 0.05. That's it, right? Now, if you take some other power setting, even there, the alpha error that you could commit is 0.05. Or to put it in another way, we have to be right 95% of the time here, right? And even if, and same thing, even for a different power setting, even for a different power setting, say 200 and 220, we have to be right 95% of the time, right? So we have to be right 95% of the time in all the six combinations. And if you multiply like this six times, because we have to be right 95% of the time, so you have to get 95% of the time right in your first t-test, and same thing for all the six tests. This will be way less than 0.95, that will be around 0.81 or something. So if it is 0.81, how much our alpha would be? Alpha would be just 1 minus of this thing, right? Which will be very greater than what we initially set out to do. So if you do separate t-tests like this, we are just compounding our type 1 error, and that is another big reason not to use t-test when we have more than two means. So that's where the ANOVA, or the analysis of variance, comes into picture here. Okay, so in order to understand this, we just have to understand the setup, which we have already seen in the previous slides. So in an ANOVA, you would have multiple treatments or multiple levels, like those could be A here, right? A levels. For our experiment, we had four power settings. So A for us was 4 here. And you can have n observations or n replications at each level. And in our case, n was 5. We tested 5 wafers at each of the power setting. Okay, so that's what we are showing here: A levels of the treatment, or A treatments, and we have n replicates at each level, and then it should be a completely randomized design. This is an important factor here. And the total runs in between would be your number of levels times your replications, which was 20 for us. Okay, so the main objective here is that we want to test whether the treatment means are equal. That is, if a given power setting has no effect on the H rate, then it shouldn't matter whether we set our machine at 160, 180 or 200. We should be getting same mean H rate at each of the power setting. Okay, so that would be a null hypothesis, that there is no difference in the treatment means at any of the power settings. Now let's look at some of the data models for ANOVA. In the first model, which is the means model, we see that the expected value of an observation in run j for a given factor level I is equal to the mean of that factor level plus error due to any unexplained variation here. So Yij here is the observation for run j at level I, at factor level I here. Okay, so if we go back here, all these treatment levels, or sorry, all these different treatments or factor levels, we can just denote them with I, where I varies from 1 to A, and all these different observations obtained in different replications can be denoted by J here, and J varies from 1 to N. Okay, so if we take Yij or if we take Y12, that denotes the observation obtained in the second replication or second run at treatment level 1 here, right? And couple of other important measures that we need to note down here are the averages at each treatment level here, right? So these could also be represented by mu I, which is the mean of all the observations at a given treatment level I here. And then the final main important measure is this one here, y double dot bar, which is nothing but the grand mean or the overall mean of all the 20 observations here, right? So that would be mu here. And this mu could also be taken as the average of all these individual treatment level averages, which will be same as taking average of all these n observations here. Okay, so these are the three important measures: Yij, observation in a in run j at a given factor level I; mu I is the mean of all the observations at a given factor level I; and mu is the overall mean, or we can also say it as the average of all these treatment level averages. Okay, so coming back to the model here, so as we can see here, so this says the expected value of a given observation should be equal to the average at that level plus error due to any unexplained variation. Say for example, at 160 power setting for 5 runs, our average was 530. Okay, so the concept of mean, as we all know, is that if we do an extra run here, say if we take a sixth run at the same power setting 160, we would expect the H rate to be somewhere closer to 530, or we would say on an average or approximately the H rate at sixth run would be around 530. So that is the concept of mean here, right? But as we can all know, we will not get exact value as that of the mean, because there could be any unexplained variation in the process due to any of the uncontrollable factors, such as the temperature around the experimental setup, or variation in the material composition of the wafer, or some unconscious error on the part of operator, right? So we'll always have to account for this error due to any unexplained variation. Now the other way of representing this relationship is in effects model here. As you can observe, the only difference is that we have split up mu I into mu plus tau I here, right? So nothing but, as we have seen in the previous slide, mu is the overall mean, or we can also take it as average of all the treatment levels here, right? So that means if we introduce a new treatment level, we expect its average to be around mu. Okay, but again, if there is any effect of the treatment error, that would be represented by tau I here. Like for example, 160 you have 530, and at 180 power setting you might have 500. If you introduce a new power setting here, say 230, we would expect the average H rate at this power setting to be equal to the average of these two readings, right? But then if there is any effect of this power setting on the average, we would want to see that, we would want to capture that, we would want to isolate that, right? So that is represented by tau I here. In ideal scenario, we would want sum of all tau i's to be equal to 0, or tau 1 equal to tau 2 equal to tau n here. That is, all the treatment effects are equal, or there is no effect of the treatment. This would be for our null hypothesis here. Okay, any of this. And this is called the one-way ANOVA or single factor analysis. Now there's another concept called fixed effects model here. So this is nothing but in fixed effects model, whatever analysis we do would be applied only to the levels that we are considering here. Say in our example, we are taking only 4 power settings: 160, 180, 220, 240. I don't remember these exactly, but let's suppose these are the 4 power settings. Okay, and we have already fixed these levels here, right? So whatever analysis we do with these settings would be applied only to these power settings here. Okay, it cannot be applied to any other power setting. So that's why it's called fixed effects model. Instead of just fixing our power settings to these 4 values, if we instead choose these power settings randomly from n different power settings, okay, that would be called as a random effects model, and whatever analysis we do, that can be applied to any power setting in a given range, right? So in this chapter and in the next few chapters, we'll be focusing only on fixed effects model. We'll touch on the random effects model in the later chapters. All right, so the null hypothesis for ANOVA would be all the treatment means are equal, or alternatively, we could say that all the treatment effects are equal and they're all equal to 0. That is, there is no effect of any power setting on the observed H rate here. The alternative hypothesis would be at least one of these two means are not equal. Then that would invalidate our null hypothesis. Okay, so similarly, at least one treatment effect is not equal to 0. So either ways, so we can form our hypothesis in either ways, but this would be most widely used because we are isolating the effect of constant overall mean here, and we are just solely focusing on the treatment effects. So in order to test our hypothesis similar to t-test and z-test, we need a test statistic, right? So we had t-test statistic and then z-statistic. Similarly, we need a test statistic here. We cannot use t-test because this is not a t-test. So we'll in the next few slides, we'll see how to obtain the test statistic that is used in ANOVA. Okay, so the first concept we have to understand is something called ANOVA partitioning here, right? So the name itself, the ANOVA, the name itself says it is the analysis of variance. That is, it is trying to see how each mean or how each treatment is varying from one another, right? So as such, we need to measure the variability here. Okay, so if you remember the calculation of variance, so variance is nothing but it's the difference between an observation and its mean, and we square this difference, then we take summation of all those all those squared differences, and if we divide by total number of observations, that would be our variance, right? And if we take square root of that, we'll get standard deviation. Okay, so we'll be following the same concept here. So this is just the numerator part of this variance calculation here, right? So Yij is one particular observation, and we are this y bar double dot is the overall mean or the grand mean here. All right, so this is similar to this numerator here, difference of each observation from the overall mean, and then you are summing those squares. So that is known as total sum of squares. So another way of writing down the total sum of squares is with respect to the difference of each treatment mean from the overall mean and difference of each observation from its treatment mean. That is, so this component for us is it's the difference of each observation from overall mean. Okay, so that is the total sum of squares for us, and this component here, it represents, so yi bar was nothing but mu I, right? So mu I minus this is mu here. Okay, so this is difference of each treatment or each level from overall mean. Okay, and then here Yij was one single observation, and this measure is the difference of each observation from its mean here. Okay, so this would be mu I for us. So this is difference of each observation from its mean. Okay, so these are important, really important measures here. So we are saying that the total sum of squares, or the difference of each observation from the overall mean, can be represented in terms of difference between the levels and difference within the level. Okay, so this is known as sum of squares of treatments, and this is sum of squares of errors here. Okay, or this can sorry, I'm trying to see if I can clear all this. All right, so this measure here that gives variability between the treatments. Okay, like how much each treatment varies from other treatment, because we are subtracting each treatment average from the overall average here. So this is between treatments, and this is within treatment or within level. All right, because we are subtracting each observation from its mean here. So this tells us in a given level how each observation is different from others. Alright, so this is a very fundamental ANOVA identity here, and as we can understand here, a large value of sum of squares of treatments reflects that the treatment means are very different from each other. If they are very close, then the variation of each treatment mean from the overall mean would almost be the same, right? So this is how you'll have to calculate sum of squares here. Again, you can follow up how they have derived this in the textbook. It's just simple algebraic manipulation. But then most of the time we won't be doing these calculations by hand. We would almost always be using a computer software to do these analysis for us, because it's just very tedious to do these calculations by hand. So from the sum of squares, we obtain the next important measures called the mean square here. Okay, so the mean square of a measure is nothing but sum of squares divided by degrees of freedom here. All right, so the degrees of freedom for the total is given by total number of runs, which is your levels, number of levels times the number of replications minus 1, and the degrees of freedom for your treatments would be your number of treatments minus 1. For your error would be based on your levels and your replications at each level. Okay, so degrees of freedom is a little confusing concept here. I thought of explaining, but then I came across this YouTube video, and I think he did a really great job in explaining the concept of degrees of freedom. I highly recommend you to watch this so that you can understand why we are subtracting by minus 1 and what are degrees of freedom and so forth. So to summarize all the ANOVA that we have seen so far, important measures are sum of squares, degrees of freedom, and mean square here. Okay, so sum of squares are nothing but, again, we have between treatments, which is the difference of each treatment mean from the overall mean, and then square of those differences, and then within treatments, which is difference of each observation from its own mean. Okay, that can also be obtained by sum of squares of total minus sum of squares of treatments here, and these are the corresponding degrees of freedom. And again, mean squares, we have seen how to calculate that. It's just dividing sum of squares with the corresponding degrees of freedom here. Okay, so this is the most important thing here, the F statistic, which is nothing but a ratio of mean square of treatments by mean square of errors here. Okay, so as we have seen, if all the treatments are close enough, there is no variability among each treatment, among each power setting, then our mean square treatments should be very less here. Okay, so if we get a very large value for F naught, that means our null hypothesis is wrong. That means the treatments are different from each other. Then we'll have to reject our null hypothesis. It is similar, the concept is similar to what we have seen in Z and T test. So this will be your calculated F statistic. Okay, so this will be F calculated, and then based on our degrees of freedom uh, and our significance level, as you can see here, F based on your significance level that we set initially, and then your degrees of freedom you will get this F critical value from F distribution table, right? And if our F calculated is greater than our F critical value, that means our values are so extreme that they will never occur if our null hypothesis is true. Okay, so we reject our null hypothesis. And this F statistic, it follows an F distribution which is somewhat like this. Okay, so it is a right tail distribution here. It's not symmetric like the normal distribution, right? So we'll obtain the F critical value based on the degrees of freedom and significance value from the F distribution table, and then we'll compare it with our F calculated value, and depending on the result, we take a decision about our null hypothesis. So if you look at the results for our example here, so all these are already calculated, sum of square of total, treatments, and errors. We need all these three to calculate the mean squares, right? So these are the mean square values here, these are the degrees of freedom, and our F calculated is 66.80. Remember, F calculated is nothing but ratio of these two mean square terms here, okay? And if we, so now next step is to get the F critical value from the table, right? So the degrees of, sorry, all right, so our significance level, by default it would be 0.05, and our first set of degrees of freedom, I'm sorry, let me go back, so that should be a minus 1 and a n minus 1, right? So that would be 3 and 16, these two, okay? So 3 and 16. So this is I don't exactly remember what page in the appendix, but it's there at the end of the textbook. Okay, so we go to the F table here, and then there is a different F table for a different significance level. We have one for 0.025, and then one for 0.05 and 0.1 and so on. But since our significance level is 0.05, we go to the table which says F 0.05 here, and then it takes 2 degrees of freedom, 3 and 16. Okay, so the first degrees of freedom is V1 here, so that is 3, and then the second degrees of freedom is 16, right? So we'll just get the value where these two intersect. That looks like it's 3.24 here. Okay, so now we compare our all right, here, so now we'll compare our observed F statistic value with our critical F statistic. So our F critical was 3.24, and our F observed or F calculated is 66.80, right? So it is way greater than our F critical value, and hence we reject H naught. Okay, we say that if H naught was true, then it is not likely that we'll see a value as extreme as this here. All right, so this is one approach. The other approach is to get the p value. Remember, we get the probability or the area under the curve for a given F value here, right? So for our F critical, we already know that our critical area is 0.05. That was our significance value, okay? So now we have to get our area corresponding to our calculated F value, and our F calculated was 66.80. So if we go back to the curve here and try to see where 66.80 might fall, you see it's way down on the right side here, and the p-value or the area under the curve is almost negligible, is almost 0 here, right? So the p-value is very, very less. The p-value for our calculated F statistic is very less than our set significance level of 0.05. So even now, even with the p-value approach, we end up rejecting H naught. I think that's it for today. We'll continue our discussion on ANOVA in the next lecture. Thank you.